Alright, so sorry I can't be there today with you this morning. I'll be back later in the day, so if you need me, you can always drop by a little bit later and I will be back. Of course, after school today I do have class, so you can drop in anytime between midday, so around lunch, and right after school, and catch me if you need me. But you're going to have to interact with me through this video. So we're going to be talking about electric potential today, and that's just really a fancy word for saying voltage. We've seen voltage before. We were talking about voltage way back when we were first doing our things about resistance in the Plato lab that we did. We figured out that voltage really just comes from the battery. Now, we're going to be doing a lab today that you picked up on the way in, and that lab is very, very similar to the current lab that we did earlier. So it's basically one of those where it says, hey, build these circuits and investigate voltage, but they don't really tell you what to do. So it looks very similar because we're going to be doing pretty much the exact same thing. We're going to be looking at a couple of circuits. So, one of the circuits that we had from last time was a circuit that kind of looked like this. And then one of the other circuits that we had was something that looked like this. Right? So we had a series and we had a parallel. So if you remember, this one is our series and this one is our parallel. Now, when it comes to the lab, right, we have to figure out what kind of question we're going to ask. And because we're just investigating voltage, then we kind of need to say, okay, well, maybe when we measure voltage, we are looking to see how it changes in a circuit. So we need to measure voltage in a number of different places and see how it changes. So for our series circuit over here, we can measure voltage. Now voltage is measured a little weird. We have to take our leads for our voltmeter, and we're going to attach them to either side of an interesting thing in the circuit. So we have our resistor there, and we just take, let's say, the red lead right here, and then the black lead right here, and we just touch it to either side of our resistor. So this is how it's drawn in. This is what we say our voltmeter is in parallel with the resistor. That's one of the things that we say because it kind of looks like this parallel circuit over here where things are attached on either side. You can see the symbol for a voltmeter is a circle with a V in it, kind of like the ammeter was a circle with an A in it. So this would be how we measure voltage across a resistor like this. So we say it's across a resistor because basically what we're doing is we're looking at a point right before and right after to see what the resistor is doing to the energy in the circuit. And this is where our voltage comes from. So we could measure it across this resistor, but of course we could also measure it across this resistor. And we could also measure it across the battery. So we would have three different measurements to take in this particular circuit. And we could go in thinking, okay, well, how is this going to change? Do you think the voltage is going to be the same for all three of these? I don't know. Think about it. Will it be the same? Will it be different? Hopefully, we will figure out in the lab. So that's the series. Of course, we could do the same thing for our parallel circuit. We could say, okay, we have a voltage across the battery. We could do a voltage across this one and a voltage across this one as well. And those aren't the only two circuits that we're going to build. These are just the series and the parallel ones. So you have two complicated ones that are also there. Now this lab was written for light bulbs rather than resistors, but we're going to use the same good old-fashioned red, blue, and green resistors from the white boxes. So to kind of give you an idea about how to do this, let me insert a picture real quick. All right, there's our picture. So you can see that this is the setup that you're going to end up seeing. So we have a couple of batteries this time. We're going to use batteries like we did last time. And you can see wires that are going around. So this will be our first circuit. This is our series circuit. So we have one of our resistors right here. We have another one of the resistors right here. And I'm currently measuring the voltage of the resistor that's on the left-hand side, the green one. So you can see the voltmeters should all be set up like they are already for you. So the black is in the column like it always is. The red is on the right side. And then you can see how we have turned the knob 3 clicks to the left, which puts it on the 20. That information is also in your lab at the very beginning of the lab. So read through the lab if you have issues. But you should also look into where we are connecting. So our circuit is connected. When we were measuring current, we had to physically remove a wire and put the meter into the area where the wire used to be. Well, in this case, we don't have to do that. Our circuit is running. It has current running through it. And all we do is touch on either of the two pegs that the resistor is hooked up to. And you'll do the same thing for this one. So you do the 2 pegs here. And then if you're going to use 2 batteries, then you would look across both batteries. So from here to, I believe it's here where we have it connected. You could also take a look at just what a single battery does. So you could do the one battery and the other battery if you're interested in that. So that would be how you actually measure the voltage in this lab. Okay, so remember voltage, electric potential, voltage, it's all the same thing. Okay, so I'm going to have the sub pause this video and let you go into the lab and take a look around. All right. Okay, welcome back. So let's take a look at what you should have looked at in the lab. So I've got some sample data, data that I took from another group. So if we're going to take a look at the series circuit first, so let's take a look at the series circuit. So if we're going to take a look here, so here's just some sample data that we took. So this was measured at 1.53 volts. That one's the battery. And then over here, we had 0.3 volts. And then this one down here was 1.22 volts. Okay, so hopefully you see something similar. I say similar because it's always going to depend on what resistors you ended up using. If you saw that the voltage here and the voltage here were the same, then you probably used 2 resistors that were exactly the same. So the same color, 2 greens, 2 reds, 2 blues, whatever. But in this case, we didn't. We used 2 different resistors. And you can see that one resistor is taking a whole lot more voltage than the other one. Right, one is much, much bigger. But what do you happen to notice about these? So this was 0.3. This one is 1.22. And if you add 1.3 to 1.22, what do you get? You get 1.53. So this is saying that our voltage that we're measuring across the 2 resistors put together should equal the voltage that the battery has. So this is bringing up something kind of interesting. So what exactly is voltage? Well, we say voltage is coming from the battery, so what is the battery doing? It's the thing that's providing energy to go into the circuit. It's providing the charge enough energy to actually move through the circuit. So this is like a gain here. This is adding energy to the circuit. The battery is 1.53 volts. Okay, so we can say it's got 1.53 volts of energy. Well, when the electron goes through that battery, so it's going to gain that 1.53 volts of energy, it's going to travel around, and then it's going to eventually get to this first resistor. Well, the resistor is not going to be gaining any energy. It's not providing the electron any energy. In fact, it's like, during class change when you're trying to go through the hallway, there's a lot of resistance there. It takes some energy in order to get through, and sometimes you feel exhausted by the time you get to the end of the hallway, especially if it's really, really packed. So the electron loses some energy as it goes through that resistor. So we'll say that that's actually a negative 0.3 volts. So it's what we call a potential drop or a voltage drop. Same thing down here at the 1.22 volts. The electron, as it goes through, or the charged particle as it goes through, will lose 1.22 volts of energy trying to get to that second resistor. So that would be like a much more crowded hallway. So this would be the higher resistor value than the other one. So it's taking a lot more energy to get through that. So why would it be that when the electron gets all the way around and gets back to where it started, it should have used all the energy that the battery gave it? Well, we can think about this underneath the guise that we have talked about before of conservation of energy. I'm not going to write it all out. We'll say coffee, conservation of energy. So what does that mean? Well, if the electron is going to gain, so it's going to start here, it's going to gain the 1.53 volts. Let's say it goes all the way around and gets back to where it started, and it still had, 0.2 volts left over. Well, then it makes another trip around. It goes to the battery, and so now it's up to 1.73 volts. And it goes around again a second time, but now it's got 0.4 volts left over. So as the electron keeps going around and around and around, it would just keep gaining and gaining voltage, or gaining and gaining energy. Well, that doesn't happen. That would be manufacturing energy. So conservation of energy says that the electron has to use all of the energy as it goes around that it was given by the battery. And if it didn't, then we would be breaking conservation of energy. So you may think, well, how does the electron know that it should use everything? Well, it's more of an equilibrium that it sets up, right? So we know that resistance will slow down current, and the total resistance in a circuit is going to dictate how much current we have. So the resistance is going to affect the current's going to affect how fast that electron goes, and so it all kind of just reaches an equilibrium pretty quickly. So this is what we call the loop rule. And this is another one of Kirchhoff's things, loop rule. The loop rule says that if you add all of the voltage gains, so do VG for voltage gains, and you subtract all of the voltage that's we lose, so the sum of our voltage losses, so VL, that should equal 0. All right, so a voltage from the battery, it's a gain, and then you have the voltage that we're losing for the resistors, those are losses. So if you were to add all the gains and subtract all the losses, then you would end up with 0. So let's take a look at the parallel circuit over here. So a data set that we got for the parallel circuit said that, let's see if we can do this in a different color. How about green? All right, so this was 1.37 volts. And this was 1.37 volts. And this one was 1.37 volts. So what are we saying about voltage in a parallel circuit? Well, it actually is all the same, right? They end up having all the same voltage. Well, why does that happen? Well, let's see if we can apply the loop rule here. So if we're going to talk about the electron's going to go through the battery. It's going to pick up 1.37 volts of energy. Now it's going to get to this point right here, and that's a junction, right? So we have to apply the junction rule, and it says, okay, well, we can either go down towards that one resistor, or we can keep going forward and go through the other resistor. So let's say we go forward. Well, if we go through that branch, it's going to hit this resistor, and that's the only resistor it hits before it gets back. So that means it has to use all of the energy that it was given by the battery. So this would be a negative 1.37 volts. Well, what if we didn't go that way? What if we came down this way? Well, it's the same thing. We only hit the one resistor before getting back to where we started, so we have to use all the energy through that same resistor. So in a parallel circuit, everything that's parallel to the battery is going to have the same voltage as the battery. And anything that is not parallel to the battery may not have the same voltage. Now, in order to figure out whether things have the same voltage or not, I employ kind of this color coding system. Now, this color coding system, you can take it or leave it. You don't necessarily have to use it, but in my head, it helps with understanding who's got the same voltage. The way that we do this is we color code the high side of our battery to be red, and anything that is touching the high side of our battery gets colored red. So any wire that's touched, that's a red wire right there. Anything that's touching the low side of the battery, the negative side, gets colored blue. All right, so we have blue wire here, and that comes over here. Okay, anything that's not touching either of those two sides will be some intermediary color. So the resistors don't get colors. We're just talking about the wires. So the wire in between the two might be orange. So this drop from a red to an orange, that signifies the 0.3, but an orange to the blue would signify the 1.22. So those don't have the same voltage drop because it goes from red to orange and then orange to blue. Now, it could be a special case where they were the same resistor, in which case they would end up having the same voltage, so you'd have to recognize that. So let's try it over here on the parallel circuit. So if we do the red, that's going from the top part of our battery, so anything that is touching the top part of the battery gets red, so that means all of these wires, which are connected to the same side of the battery, is red. And then we do the same thing with the blue, so that's all of these wires. Okay, so we know that the battery has a red to blue switch on it, or color change. But so does this resistor, it's a red to blue, and so does this resistor, it's a red to blue. So that means they all have to have the same voltage drop as the battery. So again, you don't necessarily have to do the color coding system, but for me it helps me visualize what has to have the same voltage across it. So can we take this and apply it to a more complicated scenario? So yeah, this is the circuit number 3, right? So one of the things that we had for this one was we had 2.64 volts, and on the top one we had 2.33 volts, and then down here we had 0.29 volts, okay, and 0.29. Now this is not saying these are the numbers that you should have seen, because it depends on what resistors you use. So we can see how these two resistors down here have the same potential. So let's see if we can employ the color coding system to see why they would. So we have our blue, which is going to come over here. Everything that's connected to that side of the battery has got blue on it. Okay, then we have red. So the red is going to be all up over here. All right, and then something in the middle, maybe orange. Okay, so we can see that both these resistors have the same colors on both sides, right? It's got the orange and the blue on both sides, so that means they should end up having the same voltage. And this up here has got red to orange. That means it's going to be different, as we see from the numbers. So they're going to be different. But we can also think about this, that red to blue should be 2.64. So if we take it from the red here all the way down to the blue here, that means we should end up having 2.64 volts worth of energy as well. So if we have the 2.33 volts, now we have to remember that this is a branch here, so we can only choose one way. Let's say the electron goes down this way. So 2.33 plus 0.29 does give you pretty close. It's 2.6. What is that going to be? 2.62 volts. That's pretty close. Okay, not exact, but you can explain away some of that error as maybe the wires were taking a little bit of voltage because they have some resistance, maybe a little bit. But this is showing us that if we move from a red to a blue, then we should end up having 2.64 volts of energy lost. And then we go from the blue to the red back to the battery, and so we gain that 2.64 volts back. So conservation of energy is still a thing. We still have to worry about it here, but we just worry about it in terms of the loop roll for the junction, or for the circuits. All right, so you might want to go back and take a look at some of those questions on your lab and maybe review this video. I'll have it posted to YouTube and get some really good information off that. But we're going to move on to the notes that you have. All right, so here are the pages that you have for your notes. So we're going to be doing something called Ohm's Law today. Ohm's Law and electrical potential difference. Now, where does the difference come from? The difference comes from how we actually measure the potentials. We go way back all the way over here. Our potential difference, it comes from the fact that we're measuring the red that's up here and the blue that's up here or down here and looking at the difference between the two. And so we get 1.53 volts of difference between the two. So we're just looking at the difference between one side of a resistor and the other side of a resistor. So that's where the difference comes from. So what's our analogy? Well, analogy would go back to our water system. Now we have two things here. We have a voltage gain, right? But we also have a loss that we also have to deal with, right? So the voltage gain, this is coming from our battery. And the battery is acting like our pump for our system. So the battery is what we would say is a water pump. You can think about it like we had to pump water up to the top of a water tower, right? So that we can use it later. We can get that energy back out later by letting it fall through. So that's a water pump. For a loss, then we're basically not losing it. That's actually a really bad way of saying it. We're more like converting it, right? We're converting it to other things. So maybe in the lab, if you left your circuit on a little too long, you might have noticed that the resistor started getting a little warm, right? So we're converting that energy, that electrical energy, into something else. So in the whole water analogy, we actually did this back in the resistor thing, a water wheel, right? A water wheel. What does a water wheel do on a river? Well, it takes the kinetic energy of the water itself and turns it into some rotational kinetic energy for the wheel. So we're taking some energy away from the water and giving it to the wheel. So that's what happens with a resistor. We're taking some electrical energy away from the electron and we're giving it away as thermal energy, like heat. So that's going to be our kind of our analogies here. So now that we've really talked about voltage, current, resistance, we can talk about something known as Ohm's Law. So Ohm's Law is this equation right here. I is equal to V over R. That's a little bit more than that equation. But we can look at it at this point right here. So V is the electrical potential difference. Remember that difference is just talking about before and after a resistor. Measured in volts. We have current, as we've already seen, is measured in amps. And then R means resistance. We used this way back when we first did resistance. So it's ohms, it's the omega, Greek letter, capital omega. But you can see here, because of the way that it works in the equation, it's actually a volt per amp. So that's what an ohm means in other unit systems, a volt per amp. So current is equal to V over R. So when we're connected to 120 volts of an electrical outlet, a 60-watt bulb carries a current of 0.5 amps. What is the resistance in the filament? So if I is equal to V over R, then that means R is equal to V over I. So we would do 120 volts divided by 0.5 amps, which gives us 240 ohms. We get 240 ohms. Why is the 60-watt light bulb there? Well, it's telling you what kind of light bulb it is, but we will eventually talk about the wattage of bulbs. Basically, you know that a 100-watt light bulb is brighter than a 60-watt light bulb. Remember, watts is the unit for power, so all that just kind of goes in with how quickly we're using the energy through our resistor. Now over here, when we were doing current, we had to remember that to set it up, we had to remove a wire and physically put our ammeter in there. Well, for a voltmeter, we're not doing that. We're putting it on either side of, excuse me, of our resistor. So an ammeter needed a really low resistance. But a voltmeter is going to be something a little bit different. As current comes in, it has the opportunity to go two different directions, one into the resistor and one down here to the voltmeter. Well, we don't want current to go into the voltmeter. That would disturb the entire circuit. We don't want to measure something that is going to be affected by the voltmeter itself. So in the voltmeter, we want a really high resistance. In fact, an ideal voltmeter would have an infinite resistance, so we wouldn't have to worry about current going up into the voltmeter. Now, ours are pretty good. They're not infinite, obviously, but they're pretty good, so we don't necessarily have to worry about that. But in through here, it tells you a little bit more about voltage. It says that a volt is equal to the energy consumption of 1 joule per electric charge of 1 coulomb. So a volt is actually measured in other things. A volt is a joule per coulomb. So we are talking about energy here. We're just talking about more of an energy per unit charge. But we can think about it as energy. It's basically energy. So we keep on going. So the voltmeter, so we've already done that, so that's our high, okay, high resistance. So the loop rule, so we had that the sum of our voltage gains minus the sum of our voltage losses has to equal 0. That's what we're saying. So anything that gives voltage minus anything that takes voltage is equal to 0. That's conservation of energy. So off to the right-hand side, it didn't photocopy well, and so I had to draw it in and re-photocopy it. So you can see we have a resistor here with a voltmeter on it that's taking 2 volts. We have a resistor down here with a voltmeter on it that's showing 3 volts. We have our battery that's showing 9 volts. And the idea is that we have this light bulb right here, and we want to know what the voltage drop across the light bulb is. Well, we can use the equation. So 9 volt is a gain. We'll subtract 2 volts, because that's a loss. We'll subtract 3 volts, because that's a loss. We'll subtract the voltage from the light bulb, and that should equal 0. So that means the voltage from the light bulb would be 9 minus 2 minus 3, or 4 volts. That's all you got to do. All right, we're in the home stretch. So the last part. So it turns out that Ohm's Law is not actually a law, as we'll see here in just a second. But Ohm's Law is right here. It's written in a different way. It's V is equal to I times R. And what Ohm's Law says, basically, is that your resistance should be a constant value. It tells you that resistance does not depend on the voltage drop of the current. And, in fact, that if R is constant, then that means V and I are directly related to each other. So if we were to graph I versus V, what would that look like? Well, if it's directly related, then it should be linear. And if it's linear, first question, should it go through 0, 0? Well, yeah, if you have no voltage, you're not going to have any current, so 0, 0. Now, the way that it's drawn, I versus V, what would the slope be? First instinct might say that the slope is R, but you have to remember that we're doing I versus V, so I is equal to something times V. Okay, if you were to rearrange this equation up here for I, you would find that the slope is actually 1 over the resistance. V divided by R is what I is. So the slope here is 1 over R. Now you could plot it just as easily doing V versus I rather than I versus V and get the slope of just R. Now this is true only for things known as ohmic materials, right? Ohmic materials. So the things that follow Ohm's law, that's what that means, ohmic material. So there are things that are called non-ohmic materials, okay, non-ohmic materials. So what would be an example of non-ohmic material? So the incandescent light bulbs. So those are a little bit harder to find now, but you might still have some at your house. These are the light bulbs that have filaments in them that break every once in a while. You have to change out the light bulb. These things get really hot. Okay, what really happens to the light bulb is as it gets hot, its resistance changes. And as its resistance changes, it actually increases, which causes it to heat up faster, which causes the resistance to change, which causes it to heat up faster. And so it just goes on and on and on. Eventually, the resistor has to find a different way to let go of the energy that is it's taking in, right? It's heating up, heating up, heating up. But eventually, it starts to do something different. It starts to give off light. And that's what a light bulb is. So what would a current versus voltage graph look like? Well, basically, it can only take in so much current. So it's going to be more like this. Eventually, it's going to find a different way to give off that energy, and if you put too much on it, it's going to set it on fire, and then there's a real good way to give away its energy and light and heat. Of course, it's also dangerous, so you don't want to do that. So is Ohm's law really a law? Technically, no. It's more of a rule. Okay, and science laws don't have exceptions, and it seems here that we have exceptions, or at least things that don't follow it. Now, the reason why we say it doesn't follow it is because down here it says that the essence, the real thing about Ohm's law is that R is independent of V, and that I and V are directly related. Well, that's not always the case. The non-ohmic materials don't have a linear graph. They don't have I versus V as being a linear line. So, is Ohm's law true? Sure. If we were to take any random point here and we divided the voltage by the current, that would give the resistor at that particular time or at that particular point. That would be tied to the slope of that particular line. But is it saying that it's directly related? No. It's just saying that at that particular time the resistance is a certain value. So even though we call it Ohm's law as R is equal to V divided by I, that's not entirely true. It's not really a law. It's more of just a guideline. It's a rule that we can use. And that equation is very helpful for most things. As we see up here, most metals are ohmic. All right, so we're going to hand out the homework now. So you'll have the rest of the class, however much is left, to work on your homework. You can see that there's not a whole lot on there. It's about 4 questions long. But I will remind you that if you haven't looked on the board yet, you do have a Mastering Physics that's been assigned. And it's also due by the 20th, which is Monday. And that is going to be the day that we start testing. So that means your test, being a B day, is on Tuesday. So that is what you should be looking for. But you need to get into the Mastering Physics and start getting that taken care of. I think there's 13 questions, so not bad. But remember that I'm also not going to be here for next week. I will be back this week, so you don't necessarily have to worry about that. If you have any questions, just let me know. You can always shoot me an email as well. So hopefully you enjoyed this video. I know you have a hard time not interacting with me whenever I'm not in class. Everyone's very sad about that, I know, but you guys will get over it. And I will see you guys later.